Hi, I'm excited to present StableMTL, a method for repurposing latent diffusion models for multitask learning from partially annotated synthetic datasets. Recent work leverages image generation priors for dense prediction. Marigold fine-tuned pre-trained Stable Diffusion for depth estimation and showed strong zero-shot generalization training on small-scale synthetic data like virtual kitty and hypersim. This approach extends to many dense prediction tasks, normal estimation, geometry, and 2D motion in works like Stable Normal, GeoWizard, and Stable Motion. Recent approaches show that diffusion is not actually needed for dense prediction. Lotus, for instance, trains with a unified latent MSE loss. However, these methods are mostly fine-tuned for a single task. We extend Lotus to multitask dense prediction, aiming for a more generalized approach beyond single-task fine-tuning. Traditional multitask learning requires labels for all tasks simultaneously. Partially labeled multitask learning only requires labels for a subset of tasks, but still demands multitask labels within a single dataset. We move toward a more realistic setting, multi-data set training with partial annotations, acknowledging that collecting multitask labels for every sample is challenging. Our main contribution is StableMTL, developed for this realistic multitask learning setting with 7 tasks partially labeled across 3 datasets: HyperSim, Virtual Kitty 2, and Flying Things 3D. StableMTL uses a multi-stream architecture extending the Stable Diffusion unit with task attention for cross-task information sharing, alongside a unified latent MSE loss that eliminates task-specific losses and loss balancing. We first proposed StableMTLS, a single-stream architecture used as the initial stage. It applies task-isolated sampling with a unified latent MSE loss in the latent space. Training with multitask gradients leads to performance drops as shown in the gradient norm graph. To address this, we isolate per task gradients, ensuring each update uses gradients from only a single task. This is our stage 1, training the single stream network with task tokens and isolated gradients. This stage is crucial for learning task-specific information that StableMTL leverages later. The multi-stream architecture builds on stage 1. We freeze the trained network as an auxiliary unit and add a main unit for the multi-stream setup. The auxiliary outputs serve as auxiliary streams, while most learning happens in the new main unit. To facilitate cross-task information flow, a task attention block is added to every block of the Stable Diffusion unit. Task attention uses multi-head attention. The query comes from the main unit, and the key and value come from the auxiliary unit, enabling cross-task feature aggregation. StableMTL achieves the best zero-shot multitask performance with a positive average relative improvement over the single-task baseline. It also surpasses all baselines on in-domain multitask results, where training and evaluation occur on NYUV2 for depth, semantic, and normal tasks, simulating partial label scenarios 1 and random. We visualize task interactions through attention to understand how tasks benefit each other. The attention matrix shows interaction magnitudes across layers. Strong mutual interactions appear between normal and depth, optical flow and scene flow, and shading and albedo. One-way benefits include semantic to optical flow and shading to semantic. This is confirmed further by task masking. Removing a task causes a performance drop in dependent tasks, consistent with the attention visualization. We also study the effect of task count. Increasing the number of tasks can either help or hurt single task performance, but StableMTL remains stable across combinations. The unified MSE loss is highly beneficial, achieving the best multitask metrics without explicit loss balancing, significantly simplifying multitask training. Finally, we show some qualitative results. Thank you.